Hi, my name is Ian Fogarty, and I'd like to talk to you a little bit about organic chemistry and hydrocarbons and alkanes today. Let's take a carbon and create our very simplest organic molecule. It is prevalent all over the place. Is a major contributor to greenhouse gases. It's about 25 times more potent contributing to greenhouse than carbon dioxide. So our Lewis dot diagrams look like this. So those could get together, those could get together, those could get together, and those could get together, and then we would end up with... So we end up with our very simplest organic molecule, and this is methane. M-E-T-H-A-N-E, methane. We're going to make a few of these molecules in sequence. We've already done one with 2 carbons. Let's do one with 3 carbons. There, we have all of our hydrogens have 1 electron each. All of our carbons have 4 electrons each. Now we can start making some bonds. Those will go together, those will go together, those will go together. These can go together. And we'll just double check that each hydrogen has 2. So each hydrogen has 2, 2, 2, 2, 2, 2, 2, and 2. Great. Each carbon's got to have 8 total. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So it should become apparent now that carbon is going to have a grand total of 4 bonds, always and forever. And what I think we should do is just do one more, because there's a pattern that I think is going to start emerging. And here we have our next series. We have 4 carbons, each has 4 bonds, 4 bonds, 4 bonds, 8 electrons total, each hydrogen on the outside. You should start to be able to see a pattern now. You should be able to start to see that, wait a minute, each carbon has a CH2 group, a CH2 group, another CH2 group, and another CH2 group with an additional hydrogen on each end. So you have a CH3, some CH2s, and some CH3s. So we often write it CH3, CH2, CH2, CH3. It should also point us to a general formula. We could have a question, how many hydrogens would a C2000 have if it's indeed the same kind of sequence? And that would be just a pain to try and count that out each time. So the general formula goes like this. You'd have C and however many carbons there are, and then take however many carbons you have, multiply it by 2, and then add 2 more. C2000, the hydrogens would be 4002. And C2000 is not very much. When we start talking about organic chemistry, C's of thousands and hundreds of thousands are reasonable. Even doing C6H times 2 is 12 plus 2 more 14, C6H14, it becomes a real pain to try and draw that out each time. So what we'll often do is do a condensed formula. So this is the expanded view right here. And so we might try and do a condensed view. So CH3, CH2, CH2, there's 4, there's 5 carbons, and then 1 on each end. They have the extra hydrogen on it. And that becomes much quicker. However, that's still not very fast, and so we've come up with something called a line diagram. And so the line diagram for this might look like this. So we have 1, 2, 3, 4, 5, 6. At every end or bend, there's a carbon. So there's a carbon right there, and a carbon there, and a carbon there, carbon, carbon, carbon. And we know that carbon wants to have 4 bonds. So we have just left out the hydrogens. We can figure out how many hydrogens there should be. I'll just change some colors here. So there should be a carbon right here and a carbon right there. And so that if I focus on this carbon for a moment, it's already got 1 bond to this other carbon. There must be 3 hydrogens that we haven't written, and there's the 3 hydrogens. This carbon is the second one in. It's got 1 bond to carbon already, another bond to carbon already. It wants 2 more, so there must be 2 hydrogens that we haven't written, and there it is. And that sequence continues until the end. Again, this is going to have 3 hydrogens. Using line diagrams, we can create these very long molecules very quickly and efficiently. And organic chemists have spent a lot of time looking at different kind of molecules with different carbons in different places using line diagrams. At every end or bend, there's a carbon with enough hydrogens to complete its octet. Let's take a peek at three-dimensional structure in line diagrams for a minute. Here we would have our carbon. Put our carbon in the center here. There's our methane. And we usually draw them with 90-degree angles in here, trying to separate things, because those bonds right there are really 2 electrons, and there's 2 electrons, and 2 more and 2 more. And electrons repel each other. And so we would want to try and separate them as much as possible. And on a flat dimension, that means this is 90 degrees. So we often see diagrams like this, or like this one, where the angles here are 90 degrees. However, what we don't realize is that this is not confined to 2 dimensions. We can go in 3 dimensions. So what can happen is that these can spread out. This can come down a little bit and come up. And so what we have is something that looks more like this. We have a carbon in the center. We have our carbon in the center. And then straight up we have a hydrogen, and straight kind of on the side here we have another hydrogen. And then coming out at us, this is our attempt to show 3-dimensionality. Coming out at us, we have a hydrogen, and then going back underneath the page is another hydrogen. And so this looks like a 3-sided pyramid, or a tripod with a camera on the top. It's kind of a similar situation. So when you put that in a chain, what happens is you end up something that starts to look like our line diagram, where you have our carbon here and there. And so then there's our carbon with the 3 hydrogens, carbon with 1 pointing down and out of the page, so it would be sitting on top here, and then 1 where it's underneath the page. And again here and here, here and here, here and here, and then there's my last carbon there. And so the line diagram starts to become not just a quick and easy way to draw things, but actually fairly representative on what reality kind of is. So that carbon right there is sp3 hybridized. It is tetrahedral, is the name of the shape, and the bond angle is 109.5 degrees. As opposed to if we look over here, we might be convinced that it's a 90-degree angle. It's not, it's 109.5.